Hello. It was recording. Right. So welcome to the second in this quantum laser cooling tutorial with JavaScript. And I'm using CodePen here. Hopefully you just saw a little atom thing. Let me just restart this. A little atom thing, like a model of an atom. There he is. And in the last video we gave him momentum and created him as a JavaScript object. So this video we want to get him, I can't remember what I said in the last video, but you know what, I'm just going to jump into it. What I want to be able to do straight away is tap or click in different parts of the screen and make as many atoms as we want. We'd also like to get some boundaries on here. So maybe we could reverse the momentum or something when it hits one of the screen boundaries or the browser boundaries. Right, first thing we want to do in our code, and obviously see the previous video, or that way, I don't know which way is previous. Go and see probably not that way, but go and see the previous video to see what all of this does. And I say all of it, it's not much. What have we got? Less than 100 lines. Right, so in the main part of our program, let's write a function, which is a p5 function, and I'm just trying to remember what it's called. It's called mouse down, I think. Mouse down. It's mouse pressed. Okay. It's coming back to me. It's coming back. So mouse pressed, and then basically we want to create a new one of these objects. We want to instantiate a new one, and to instantiate the first one, in the setup function, we just said Higgs equals new atom, and then in the draw loop, remember that's a loop, because we're using the P5 library, this function loops around, and we're jiggling the atom, we're updating it, and we're rendering it. So really we want to do that for an array of atoms. So let's make Higgs not just a singular atom, but an array, and to create an array we use this syntax. Okay, and things are kind of things are still working somehow. Okay, well done JavaScript, you're still working. So we can delete him. You know what, we can delete this, and what we could say is Higgs push, so that's to add a new object onto an array, push, and what do we want to push? We want to push a new atom, and by writing new atom, that will create a new atom object using our code, I believe. Right, so we're not seeing anything on screen now, so either this is wrong, or we need to now update our draw loop. So we want to iterate over or loop over all of the objects in our array and jiggle, update, and render them. So let's just write a for loop. For I've forgotten how to write for loops. Let I equals 0. Is that right? Do you do it like that in JavaScript? I is less than. Now we just want to ask for the length of the array, and that way we can update the length of the array and we won't have to update this part of our code. So to access the length of an array, you write the array's name. Our array is called Higgs, and then write dot length, and we want to do that, we want to increment by 1, so I++. Okay, and then we want to do the following. We want to say Higgs I, so using the square brackets we can refer to a specific object on the array. And now we've got our, I was going to call it a Higgs boson, we've got our first atom back. So now this code, we've just changed this in the draw loop using a for loop, and we've just replaced our our variable like a, what do you call it, like an empty variable. We've replaced it with equals empty square brackets, which means I want Higgs to be an array of some things. We're pushing onto that array just one atom at the moment by using a new atom here, that phrase, which we kind of used before. So you know how it works from the previous video. So now what we can do, in mouse pressed, I can say Higgs push another new atom. There we go. And I think that will be created just at the center of the screen. Yeah, let's have a look. Yeah, there we go. This is already quite fun to play with. And you can kind of see that we've got a particle system. Quite like that. We've got a particle system because our like a random particle system. It does look like a gas, and it is behaving like a gas. It's kind of filling the space. Isn't that what I get? Oh, that was quite good. One comes back. They're almost like little creatures because they can turn around and things. There's no other forces involved yet, which gives the illusion that they are making up their own minds. And who's to say they're not? Who's to say that I haven't just invented consciousness? Who's to say? Anyway, one just snuck up from the bottom of the screen. Right, what we want to do is actually change where they appear. We want them to appear maybe, although I quite like them appearing at the bottom of the screen. We could have them appear where we click or where we tap. We could do that in a clever way. We could say if you double tap, then they appear where the mouse is. Let's just try it simply. So let's have a look at our atom class. The constructor is the important function for us because that's where the object, the atom object, gets created or initialized with its member variables. So its member variables are its position, or this.pos, its acceleration, this.ac, and this.vel for its velocity. It's also got a radius. Right, that's all the variables. So we want to change its position. So its initial position will be, by default, this. So when this constructor function is run, every time you create a new atom, or instantiate a new atom, it just places it halfway across and halfway up or halfway down the screen. So we could pass in some variables here. So let's pass in an x and a y, and we can say x and y. So now when they're created, they should be created at 0, 0, which is the top, am I pointing in the right direction? Top left of the browser window, or the canvas. That's 0, 0. Okay, so if we create our first atom, so back in the setup function, we can say we want you, I'm going to put this on a new line just so that it doesn't break in a strange place. We can say we'd like you to start in the middle, width divided by 2 and height divided by 2. So our first one, starts in the middle, and then the subsequent ones start at 0, 0, because when the mouse is pressed, it's just creating it 0, 0. So we could say, in here, we could use the P5 keywords mouse X, guess what that does, and mouse Y. And now let's see, yes, wherever we tap now, or click, we get a new atom. So mouse X and mouse Y, if you've got the P5 library attached to your JavaScript file, then they will hold the mouse positions. Right, brilliant. So we've got a bit more control over things. Yes, oh, we can still do the particle system thingy by just clicking in the same place. That's really cool. We've got kind of semi-transparent particles. Yeah, brilliant. Okay. Right, so now I don't mind that they're kind of floating around and things like this. Let's get the laser working. So what the laser wants to do is, if it detects the atom moving up, it wants to add some momentum in the reverse direction until the atom kind of freezes. So it would be good to kind of press the space bar or something like that, and we get the laser working. We also, it would be nice to kind of like see the laser lines as well, so we can kind of visualize what's going on. Okay, right. I don't know where to start. Well, let's think. Every draw loop, we want a laser to basically ask the question, are these Higgs particles moving towards me? And it wants to check all of them. Okay, so we need a function really. I want to say, well, you know what, we could put it in our loop already, because we want to iterate over all of these atoms. We want it to jiggle, but also we then want to zap with laser. Okay, so we want to say okay, we'll just call the function zap, and what we'll pass into the function is the current atom object. So we're just going to pass in the entire object. Okay. Right, so we need to go write that function zap, and so it takes an atom which we'll just call A. Okay. And just to remind ourselves, A is an atom object, so we remember. And then we want to, let's first check up momentum, up mom. We're first going to check up momentum. So we're going to say if A's, now we want its acceleration. Let's use that. Oh my god, I don't know what momentum is. Momentum equals, I don't even know, velocity times something by its weight, I guess. Let's have a look. Let's go on the internet. Momentum. Because whenever I hear people describing this laser cooling thing, they oh, I'm looking up labour momentum. Right. No, I want the physics, please. Oh, here we are. Mass times velocity. Okay, in terms of an equation, the momentum of an object is equal to the mass of the object times the velocity. That's very easy. Mass times velocity. Right. So we need a mass. We haven't got a mass. So we'll just treat the mass as 1, I guess. So it's basically it's velocity. The velocity, that's what we're looking at. But we're going to change its acceleration, because when you're dealing with a simple physics system like this, you only want to affect things via forces or via acceleration, which will impact the momentum. Okay, so right. Okay, so if A's after all that I put in velocity, so acceleration. If A's acceleration, and what component of the acceleration we want? We want the y component is less than 0. Then we basically want to zap the atom. So we kind of want to do, let's try and draw that line. Should we do it red, I guess? Obviously lasers are kind of red. So we want stroke, which is the line color. Red, we'll just say I'll say 250. I don't want to go 255 straight away. 0, 0. Okay, there we go. Also, stroke weight, the thickness of the line might be important. Let's just try 3 because it's a magic number. And then we want to go from the top of the screen, but at the atom's x location. So .pos.x. And then we want the, you know what, I'll put this on the same line so it's easier to read. Then we want 0, that's the top of the screen, to the, let's say, the center of the atom. Nucleus, if you will. So we'll say a.pos.x atoms.pos.y. So that's the very center of it. Aha! We've actually got a laser firing already. That's kind of cool. Would it look better if it wasn't at the center of the atom? I think it would. So we'll say that minus the radius. So it's rad. There we go. It might be the radius divided by 2. And that should be approximately the edge of our atom, which looks a bit better, I think. Okay, it actually looks like it's doing something, which is not at the moment. It's just pretend. So we want to... Oh, we can add more. That's kind of cool. So then we want, no pun intended, then we want to actually add a force when the laser hits, so, or appears to hit. So we want to say A's acceleration in the y direction, it wants to have something added to it, which will give it a down movement. Because at the moment this question is asking, is its y movement negative, i.e. going up the screen? So we want to say plus equals, let's say laser strength. So ls will be our laser strength. So we've got an error there, we've got a bug there because ls does not mean anything at the moment. But we can change this up here. Let ls equal 0.1, let's say. And it's pushing it down quite happily. There we go. I've just noticed something, and you're probably wondering this as well. This is only supposed to happen when the atom is moving upwards, which they're clearly not. So we shouldn't see any laser beams. So what's going on here? I'll go back down to zap. If it's acceleration, okay. So we don't want to talk, oh, we do want to talk about velocity there, don't we? We only want it to fire if it's actually moving upwards. So its acceleration can be different things, but it's movement, it's velocity. Okay, but we do want to impact only its acceleration because that's, as I explained, appropriate for a physics system. Okay, this is looking kind of cool. Right, again, no pun intended. Right, so now we want to do kind of the opposite thing. We want to check the down momentum. Let's just do something crazy. Let's do its left momentum going this way. Okay, so if its velocity x is less than 0, should we have a different color laser? Okay, red, green, blue, 250. The weight will be the same. Now we want a line from we draw it from the left hand side, so it wants to be 0, and then we want to just match the atom's height in terms of its position, its positional height. Then to, its x location minus a dot rad divided by 2, so that's the edge of the atom, and then we want to match its y position exactly. There we go. And then I want to make this neat. Oh, and then we want to add acceleration to its x component, and we do want to push it. So we should now push down and to the right. Okay, I guess we want a white laser going up, and I don't know, what color laser do we want going? I don't know, yellow or something? Right. So I can basically copy both of these now, and I just need to change the colors and change the polarity of direction. So if x is greater than, so this is first check, movement right momentum, and this is down momentum. Let's do the fiddly bits first. X plus that to put it on the edge of the atom, and then minus the laser strength. And then we want, what color did I say? Yellow, red and green, I think. 250, 250, 0. Oh, and the line wants to go from all the way across the screen, not from 0. There we go. And I actually made yellow. That's a surprise. And you can kind of see it's centering on its position. That's cool. Okay. And now we want them corrected from the bottom. So if its velocity, its speed, is greater than 0, which means it must be moving down, then stroke color wants to be close to white, 250. It wants to go from, not 0, but from the bottom of the browser window, and it wants to be at the edge of the atom from the bottom, so plus the radius divided by 2, and we want to subtract or decrement the momentum. So there we go. We've achieved laser cooling. I'm not sure if it's quantum. I just put that on there to sound good. What would be good is two things, I think. One, to only switch the laser on when we want it to be switched on. So let's try to write that in now. So we want to say something like, we'll have, oh, I need to label this up so I know what I'm talking about. This is the laser strength. This is our array of atoms, and then we want, is the laser on, I'm gonna call it zap on. There we go. Can I say false straight away? I think I can. And then I can say, in the draw loop, here we need to say iterate over all atoms and do their physics. There we go. And then we want to zap with the laser only if, we want to say if zap on, then do that. So this should now stop because the laser is switched off. Okay, you know what? Now that I've basically broken it somehow, I'm going to stop there, and in the next video see if we can switch on and off the laser and then tidy up the boundaries and things like that. Okay, right. Thanks very much. See you in the next video. Do put any comments if you've got any suggestions. Thank you. Goodbye.